When engineers, scientists, and analysts, as well as other professionals, model their work with functions, often they compose functions together. And when they wish to find the optimum value of the function, they need to use the chain rule to find the derivative. Hi, my name is Jason Rosenberry, and that's the topic for today. Let's take a look at the chain rule. The chain rule. If f is differentiable at the point u equals g of x, and g is differentiable at x, then the composite function f of g of x is differentiable at x and is found by the following. F of g prime of x is equal to f prime of g of x times g prime of x. In Leibniz notation, if y equals f of u and u equals g of x, then dy dx equals dy du times du dx, where dy du is evaluated at u equals g of x. The composite function version of the chain rule can be thought of as differentiating the outside function, evaluated at the inside function, and then multiply by the derivative of the inside function. Let's try some examples. For the following, find dy dx. Number 1, y is equal to the quantity x plus root x all to the negative 2 power. Number 2, y equals sine x to the negative 5 minus cosine x cubed. Let's look at the first problem. We have y equals the quantity x plus root x to the negative 2. So to find y prime, using the chain rule, here we have a function to a power. So first step is differentiate the function to the negative 2. So differentiating, we get negative 2 times the function x plus root x, decrease exponent by 1 to the negative 3, and now we got to go back inside and take the derivative of the function. So this is times derivative of the function, which would be 1 plus the square root of x is x to the 1/2 power, so we can think of that as the derivative being 1/2 x to the negative 1/2. And now we'll simplify. So we have y prime equals negative 2 times the quantity x plus root x to the negative 3 times 1 plus, and we can write 1/2 x to the negative 1/2 as 1 over 2 root x. The second problem was y equals sine x to the negative 5 minus cosine x cubed. So to find the derivative of y prime, we will differentiate each term. So the derivative of sine x to the negative 5 would be negative 5 sine to the negative 6x. Now go back inside and take the derivative of sine x, which is cosine x. Multiply those together. Minus derivative of cosine cubed x would be 3 cosine squared x times the derivative of cosine x, which is negative sine x. And now we'll simplify. So y prime is equal to negative 5 sine negative 6x times cosine x plus 3 cosine squared x sine x. Let's try another. Find the value of f of g prime at the given value of x. Let's say that we're given that f of u is equal to 2u over u squared plus 1. We're also given that u, which is the same as g of x, is equal to 10x squared plus x plus 1, and we want to evaluate all of this at the x value, x equals 0. The first thing that we'll do is let's evaluate g of 0. Since x is equal to 0, then our u value, which would be g of x, or in this case g of 0, is 10 times 0 squared plus 0 plus 1, which is 1. So we know that u which is the same thing as g of 0 is equal to 1. Now let's find the derivative of f of u. So f prime of u would equal denominator u squared plus 1 times the derivative of the numerator, derivative of 2u would be 2, minus the numerator 2u times the derivative of the denominator, which would also be 2u, all over denominator squared. So u squared plus 1, the quantity squared. Now let's simplify. F prime of u would equal, in the numerator, 2 times the quantity u squared plus 1 would be 2u squared plus 2 minus 2u times 2u, 4u squared, over denominator squared. So I have u squared plus 1, the quantity squared. And this would equal, in the numerator, we have negative 2u squared plus 2 over u squared plus 1, the quantity squared. Now that we have f prime of u, let's evaluate f prime at our u value, which we know u is equal to 1. So let's evaluate f prime of 1. So that would be negative 2 times 1 squared plus 2 in the numerator, and 1 squared plus 1, the quantity squared, in the denominator. So we would get in the numerator negative 2, that's 0 over 1 squared, 1 plus 1, 2 squared, over 4. So the answer is 0. Let's try another example with more links in the chain. Find dy dx for y equals the quantity 1 plus cosine squared 7x, all of that cubed. So we'll start by thinking of this as some function to the third power. So differentiating, we would get 3 times the function 1 plus cosine squared 7x, decrease exponent by 1, giving us 2. Now we have to go back inside and take the derivative of the function. Derivative of 1, 0. The derivative of cosine squared 7x would be 2 cosine 7x times the derivative of cosine 7x, which is negative sine 7x. But now we must also go back inside and take the derivative of this inner function. And the derivative of 7x is 7. So we multiply by another factor of 7. And now we simplify. So y prime would equal negative 42 times the quantity 1 plus cosine squared 7x squared times cosine 7x times sine 7x. We use the chain rule to find the slope of a curve given parametrically. Let's take a look at a formula for this. Finding dy dx parametrically. If all three derivatives exist and dx dt is not 0, then dy dx equals dy dt divided by dx dt. Let's try an example. Find the equation of the line tangent to the curve defined parametrically by x equals secant t, y equals tangent t for values of t in the interval negative pi over 2 to pi over 2, non-inclusive, at the point root 2 comma 1 where t is equal to pi over 4. So we have x equals secant t, y is equal to tangent t, t is equal to pi over 4, and we're given the point root 2 comma 1. Let's begin by finding dy dx parametrically, which is by definition is dy dt over dx dt. The derivative of y with respect to time, which means the derivative of tangent t, is secant squared t. So the numerator is secant squared t. over the derivative of x with respect to time, or with respect to t. The derivative of secant t would be secant t tangent t. Secant t tangent t. And now we'll simplify secant squared t over secant t tangent t. We have a factor of secant t that divides out, leaving us with secant t over tan t, and that simplifies to cosecant t. Let's now evaluate our derivative dy dx using t equals pi over 4, and the cosecant of pi over 4 is square root of 2. Cosecant of pi over 4 is root 2. So there's the slope of the tangent line. Slope of tangent line is root 2. Let's now take the slope, root 2, and we'll now use our point, root 2 comma 1, to come up with the equation of the line. So we have y minus 1 equals root 2 times x minus root 2. That gives us y minus 1 equals root 2 times x minus 2. And now adding 1 to both sides, we get y is equal to root 2x minus 1. Now it is time for you to try a problem. Find the equation of the line tangent to the curve defined parametrically by x equals 2 cosine t, y equals 2 sine t, at the point where t is equal to pi over 4. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So we have x equals 2 cosine t, we have y equals 2 sine t, and we have t is equal to pi over 4. Let's first find our point x comma y by substituting pi over 4 in for t with our two equations for x and y. So x equaling 2 cosine t would equal 2 times the cosine of pi over 4. The cosine of pi over 4 is root 2 over 2, and root 2 over 2 times 2 is root 2. Likewise, for y, we would get 2 times the sine of pi over 4. The sine of pi over 4 is root 2 over 2, and again times 2, we get root 2. So the point would be root 2, root 2. Now let's find dy dx, which is equal to dy dt over dx dt. So the derivative of y with respect to t would equal 2 cosine t, and the derivative of x with respect to t would be negative 2 sine t. Now let's simplify. 2 over negative 2 is negative 1, and cosine divided by sine is cotangent t. Now to find the slope of the line, let's substitute pi over 4 in for t, and negative cotangent pi over 4 is negative 1. Now let's find the equation of a line that passes through the point root 2 comma root 2 and has slope of negative 1. So we have y minus root 2 equals slope negative 1 times x minus root 2. That gives us y minus root 2 is equal to negative x plus root 2. Adding root 2 to both sides, we get y is equal to negative x plus 2 root 2. In this lesson, we extended our study of the chain rule and applied it to curves defined parametrically. Be sure to work the exercises that your teacher assigns. We'll see you next time.